Good morning, everyone. Welcome back. So we're going to finish up with our discussion of the Rubik's Cube by looking at one aspect of these position vectors, four tuples, that we haven't done so yet. And that is to try to figure out how we can take a four tuple, two four tuples, in other words, and combine them together to produce a composition of the moves. So, what am I trying to get at here? So if we think back to the swap puzzle, which we started off with. So what we did was we said, okay, with the swap puzzle, we can encode a configuration as a permutation. So, let's just draw a real quick one up here. So for my swap puzzle, maybe that was box 1, 2, 3, 4. And really, we've done this for all our puzzles. And if I throw the numbers in 1, 2, 3, 4, let's say, there's the configuration. We said, well, we can represent this as a permutation. So alpha would be the object that started in position 1 is now in position 3. Tile 3 is now in position 2. Tile 2 is in position 1, and 4 has gone to 4. So we can encode the position as a permutation. And then the next thing we did was we said, hey, what we could also do is encode a move as a permutation. And what was the way we did that? Well, we said wherever the tile was, where it originally started before you did the move, figure out where it ended now. So in this case, I would summarize this as if I went from the solved state to this state, the tile that started in position 1 has gone to position 3. The tile that started in position 3 has gone to position 2, and so on. And so I get the same permutation, thinking of it not only as a static thing, but also as a representation of the move that happened. And then we saw that as we did a move and then another move and another move, we can just multiply the permutations together. And that will give us the permutation, which represents the configuration of the final state. So that was very nice, because permutations not only represented the configuration of the puzzle, but they also represented moves. And then we could multiply them. We want to do the same thing here. We have these position vectors, these four tuples that represent the state of the Rubik's Cube. So suppose I had two of them. I had an X position vector, which was rho sigma VW, and I had a Y position vector, rho star, sigma star, V star, and W star. Now I think of X as the position vector that I get from going from the solved state to the particular state I'm in. So now I can not only think of it as a static object, it is actually a representation of the moves that happened. So it's the representation of the move sequence that took the solved state to X position. And Y is also a representation of the move sequence that took us from the solved state to Y. But then I can ask, well, what happens if I did the move sequence that got me to X, and then I followed the move sequence that produced Y? Then what would I get in the end? So in other words, before I did the Y moves, I actually started with the puzzle in the configuration that X left off. What do we get when we compose X with Y? That's what we want to work out now. So if I think of X as now a move sequence and Y as now a move sequence, from those four tuples, can I find a four tuple that represents the configuration after doing them together? In other words, I'm trying to come up with a group operation on these four tuples, a way to combine these four tuples to produce a new four tuple representing the composition of the two moves. So let's think our way through how this would work. A couple of them will be straightforward. A couple of them will be a little bit of a mind bender to try to figure out, but we'll think our way through it. So the whole time I'm thinking of, I've done the sequence of moves that gives me configuration X. and then I do the sequence of moves that I would have done on the solved puzzle to get to y, but now I'm doing those same sequence of moves starting with where x left off. So now I want to think, how can I build my new permutations? So what does x followed by y do to a corner QB? Now I'm going to build my permutation up. So corner QBI, where does it move when we do this combination of x's and y's? Well, corner QBI, it's going to start in the, so we're imagining we're in the solved state. Move x takes corner QBI and moves it to row I. That's where x moves corner I to. So x moves corner I to position row I. That's what the permutation row is actually encoding. Now I've got corner QBI sitting in position row I, but then I do move y on that one. And so now I have to think, now I've got a corner piece that's in position row I. What does y do to that? Well, y takes the piece that's in position row I and moves it to position row star of row I. This is just a combination of permutations. The first permutation takes I to row I. The second permutation takes it to row star of row I. And so what we get is that this is, now if we think about the way we do our composition, this is going to be row star first, and then, sorry, row first, and then row star. We read this from left to right. So this is a row star of I. Okay, so that means that in order to figure out, starting with move x, then doing move y, what is the first component of the four tuple? It's just going to be the product of row and row star. So nothing surprising there. It's really just a swap puzzle. A piece moved from this position to that position, and then the next move moved it to that position. And so the result is that it moved as a product of the two permutations. Same thing with the edges. It's sigma star, sigma I, or in other words, sigma star of I. So that's how the edge pieces have moved around. Now the fun part. How does the orientation work? I start with a corner piece I, and what I want to do is try to figure out what is the number, what is the label on the corner QB that's in the primary faucet of the cubicle that it's now going to sit in. So this is where it takes a little bit of thought to sort of trace through what happens. So I got a corner QB. It's starting out in the solved state, and it's in its proper orientation. When I do move sequence X to it, that takes that corner QB. It moves it to location row I, and that's fine. We've already taken into account where it moves to. So it moves to location row I, but it's got orientation number VI. That's the orientation number, in other words, the number on the sticker, 0, 1, or 2, that's in the primary faucet of the location it now resides. But that's only the first step. Now we do another move sequence that takes that corner piece and moves it somewhere else, potentially twisting it some more, rotating it some more. So how do I figure out what the orientation number is? Well, let's think for a moment. If the cube has moved from the solved state to the intermediate location, so that first step after X, it's now in its new location X, and it's got a 0 in the primary faucet, then that means it's properly oriented. So when I do the next move sequence, it's going to take that corner piece, move it somewhere else, and it's going to get the orientation number that it would have had if that was the original cube in that spot. So in other words, it gets orientation number V star of whatever that position was it started from, which would have been row I. But if the corner QB didn't have a 0 in that location, it was like rotated so that it had a 1 in that position, then that just means that it's bumping the rotation up by 1. Or if it had a 2 on it, it bumped the rotation up by 2 because it would move to the new location and it would already be rotated 2 clicks. So I'd have to add that to the rotation number that it got from the move sequence. So in other words, it's the starting number that's on its sticker in the primary faucet of the location it just moved to, plus it gets the number that the next move gives to it. And since it's in location row I, it's going to get the number that the next move gives to the cube in row the row I position. So this is what the label is on the ith corner QB of the location it lands in after the 2 moves. It gets a VI to start, and then it gets the V star row I as the next number. And it's the sum of these two mod 3 that we get in the end. So that's, I'm not expecting you to get this all in one go. It does take a little bit of thought as to figure out, you know, what happens at each stage. You do a move, it moves somewhere, how did it rotate? And then the next move, it rotates a little bit more. We have to add those two numbers together because that's how it rotated in the end. But it's the first number is the VI number. So how the ith cube rotated. The next number is how the QB in the row I position gets rotated, because that's where the ith cube is right now. It's in the row I position. And then next we get the same thing here. It's a WI plus W sigma I star. That's for the edges. And this would be mod 2. So mod 2, because if it had already been flipped and then it got flipped again in the second move, then it would have been flipped twice. It would have had a 1 plus another 1, which is 2. But flipping twice means the zero's back in there. So it'd be 1 plus 1 is 2, which is equivalent to 0 mod 2. Okay. That means that we can find the 4-tuple for the combination of moves x, y. The 4-tuple would be just the product of the permutations for the corners, the product of the permutations for the edges. Those are just how the pieces got permuted. It's the flips that really take a little bit of consideration. And the way the flips happen is it's going to be V plus, and I'll write this down. I haven't defined this notation yet, but I'll do so now. It's what we call V plus rho V star, and this would be W plus sigma W star. What do I mean by rho V star? So that's a permutation acting on a vector. So where the permutation acting on the vector is the permutation, the vector is V1 star, V2 star, all the way up to V8 star. So that's just the 0, 1, or 2 in each of those components for this move y. And rho acting on that is just going to permute these numbers. It's going to permute the entries of the vector. And the way it does it is it just acts on the subscripts. So it's row of 1, row of 2, row of 3, all the way down to V sub row of 8. So all it does is rho acting on those just permutes the numbers in there. And that's just so that when we add them up, we get the number we want. Because what we want to do is we want to add these things right here. We want to add VI, the ith component of the first vector, with the row ith component of the second vector. So what I do is I take that second vector V star and I permute them so that the things I want to add to VI are in the right component. And so that's why we're doing this permutation of those things. And similarly, sigma of W star is sigma of W1 star all the way up to W12 star is equal to W sigma 1 star and so on down to W sigma 12 star. Okay, that's just the gory little nitty-gritty details of what these things actually mean. But here's the big picture. So I start with two move sequences, so a bunch of moves that I can do that are called X, a bunch of move sequences of twisting faces that I call Y. And if I want to do all of the X moves first and then follow them with the Y moves, if I know what the 4 tuples are for X and the 4 tuple for Y, then I can get the 4 tuple for their product in this way. It is just the product of the permutations in each of the first 2 components. And then it's this modified sum of the V vector and the V star vector. It's the V vector added to a permuted V star vector. And it's the W vector added to a permuted W star vector. And that gives me my new orientation vectors. So that's what we call the group operation on RC3. So if I work with RC3 and these 4 tuples and I want to start to multiply them together to produce new puzzle moves, then this is how the multiplication gets done. And it's just sort of twisting that happens in the second, the third and fourth component. Okay, so that's all I really want to say about that. This is sort of stepping into much more complicated territory than I want to get into for the Rubik's Cube. But it's certainly now at a point where you can, if you understood it up to here, then you can understand a lot more of the higher level theory of the Rubik's Cube that we're just not going to touch on. I think we've exhausted what we want to do with the Rubik's Cube in this course. But what do I mean by higher level theory? So now if you really want to explore RC3 as a group, what is the group operation on it? Now we've got that. Now you can look at subgroups of this thing. You can try to explore RC3 as a group in and of itself, Cayley tables and the whole bit, and really start to understand it. And then how to write a program to solve the Rubik's Cube. That would take into account these kinds of things. However, I just want to finish on one question because I think this is a really cool question. And I'm going to do a calculation first. So the reason I'm introducing that stuff there is because I want to do this. So for any group, there's this notion of what we call a center of the group. So I'm just going to comment out this because I'm just going to use the scripting window rather than open up a new syzygy window to do all these calculations. So there's this notion of what's called a center of a group. And what the center of the group is all the elements in the group that commute with every other element of the group. So for example, if we had an abelian group where every element commutes, then the center is the whole group. I mean, there's not much new there. If you had the group of permutations, like the whole group of permutations, let's say S5, all permutations on 5 objects. Well, we've already proven very early on in the course that for any permutation you have, you can always find another one that doesn't commute with it. So for example, the symmetric group on 5 objects, the center would be trivial. Only the identity commutes with every other element. So we can ask in the Rubik's Cube group, is there an element in the center, or what are the elements in the center? And again, the center is just those elements that commute with every other element of the group. So it doesn't matter if you had an element in the center, it doesn't matter if I did it first and then another move sequence, or if I did that other move sequence first and then the element to the center, because they would commute with each other. And so our question is, what is the center of the Rubik's Cube group? And let's evaluate. And I want you to pay attention how quickly this happens. So there is our center. And part of the lag was just because I'm asking a server to do that. If I did it on my own local installation of Sage, it would come back even quicker. But it says it's a subgroup generated by, and if I look closely, I see it's a whole bunch of 2 cycles. So that's one element. So that's just one element, because there's no commas between any of these cycles. So let me just highlight it. That's one element. So it's a subgroup generated by this one element. And that one element is a product of disjoint 2 cycles. So that one element is order 2. So the subgroup generated by an element of order 2 is just a subgroup of size 2. So there's only 2 elements in the entire Rubik's Cube group that commute with every other element of the group. The identity is an obvious one. So we've got the identity. This one we're staring at is the other element that commutes with every other element in the Rubik's Cube group. Now, this is kind of miraculous that this came back so quickly, because we are searching through a group of 4.3 times 10 to the 19 elements. This is not an exhaustive search that happened here. What happened here was something very structured in the background, the ability to find the center of a group. That is so huge, and to come back so quickly. This is a whole other area that we could have focused on, but we aren't. And that is writing algorithms, computer algorithms, to do computations in groups. So this is computational group theory. We've sort of treated it as a black box here. We fed some stuff in, we queried for the center, it came back. So there's a lot of power that went on behind the scenes to come back with this center. Same with things like when we asked for the order, there was a lot of machinery that was going on behind the scenes to come back with the order, but we got it, we got the center. And so now I just want to take a peek as to what this thing is. So it's a bunch of 2 cycles. So this says 234, they have swapped. So I'm going to scroll back up here and look at my diagram. 234. Okay, so that's the edge that's in the up back position. So that flipped. So that edge flipped. 2 went to 34, 34 went to 2. 410, 526, let's keep looking around. 410, okay, so that edge flipped. 526, that edge flipped. So we can even see that on this picture up here. 526, that edge flipped over. I'm guessing then there'd be a 718 2 cycle as well. Let's look. There it is, 718. And if we read how many 2 cycles there are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 2 cycles. Each one of them represents the flip of an edge. And so what this is telling us is that the only other configuration or a move sequence on the cube that commutes with all other Rubik's Cube moves is this sequence that produces a flip of every edge. And so we call this the super flip. And I'll hold it here. I've got my cube already in the super flip position. So all it is every edge, you can see there's a blue and a red here. The edge between them has been flipped. There's a yellow and a red. The edge between them has been flipped. So this is a configuration where the permutations are all the identity. Rho is the identity, sigma is the identity, because every cube is back in its home position. It's just not in its proper orientation. All the corners are, but all the edges have been flipped. So this is known as the super flip. And it's important for a couple of reasons. One, it's a position that is the furthest away from the solved state in terms of optimal moves to solve. So 20 moves suffice to solve the cube. This is one of those configurations that's furthest from the solved state. So it takes 20 moves to solve it, minimum 20 moves. So the best case scenario, if you solve it optimally, 20 moves will do it, and you can't do it in less. But the other reason that's important is because it's the only configuration that commutes with every other move. So I've done the super flip here. Now let me twist a face. I will twist the yellow face. So I will twist it clockwise. So I'm twisting it clockwise. So I did super flip and then a clockwise twist of the right face. Now I'll do super flip again because it's order 2. It's like doing its inverse. So I'll do super flip again. I'll just do it as 2, 3, 4. and then 1, 2, 3, 4, and then 1, 2, 3, 4. And then I'll hold my puzzle so that it was in the orientation I had before. So I did super flip, twist to the right face, super flip, and we see that that's just equal to a twist to the right face. And that's because super flip, twist to the right face, super flip, I can rearrange them and just do super flip, but it's order 2, so those would cancel out. So that's equivalent to a twist to the right face. So that's what I mean by it commutes. If I do super flip, any other move, followed by a super flip, that's just equivalent to the move that I did sandwiched in between. So that's what I mean by it commutes with every other move. Now here's the thing. We've just established that the super flip is the only one that commutes with every other move by using a computer. We can actually do this using our way of computing products using these position vectors. And so that's what I want to do now. I'm actually going to show that the super flip is the only thing that commutes with every other element of the Rubik's Cube, thereby establishing the proof that the super flip has this property without having to rely on a computer to do the calculation for me. We can do this by hand. So I'm just doing a recall. Recall the center of a group is denoted by capital Z of G, and it's just the set of all A in the group such that they commute, or that A commutes with every other element of the group. So AG is GA for all elements G of the group. So let's find the center of the Rubik's Cube group. Okay, so the first thing I want to just note is that I've drawn the super flip here, and it has the property that both permutations are the identity, the corners are not twisted, whereas the edges are all flipped. So that's the constant vector 1. In other words, it's 1, 1, 1, dot, 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 all the way down to 1, 1. So every edge has been flipped. That's what the super flip is. Let's prove that it is in the center. Okay, so how are we going to do this? We are going to let X be an element of the center of RC3, and we will write it as X equals rho, sigma, V, and W. Okay. Because it's in the center, what this means is for any Y, which is rho star, sigma star, V star, and W star, we have that XY is equal to YX. That's what it means to be in the center. It means X commutes with every other element. And so that means that what is XY? XY is rho, rho star, sigma, sigma star, and then those other two entries are those twistings, or the orientations, and we've got to remember how to do those. That's up here. That is this equation. Maybe I'll start in pink. That's this one here that tells us how to multiply these things. It is take the V vector for the first one and add it to the permutation rho of the first one of the V star of the second one. So it is going to be V plus rho V star and W plus sigma W star. And then that's equal to the product in the reverse order. So that would be rho star, rho, sigma star, sigma, V star plus rho star V, and W star plus sigma star W. Whew. Okay. These things have to be equal. And they have to be equal equality holds for all rho star, because that's the y, the y components, which I'm just taking to be any element of RC3. So it has to hold for all rho star in S8, because for the Rubik's Cube, we can have any of the 8 factorial permutations of the corners are possible. And it's also got to hold then for all sigma star in S12. Any of the sigma star permutations are possible. It's just that you can't have the rho stars and the sigma stars being anything at all. They have to match in their parity. But there is any rho star possible. I could take rho star to be any permutation, and then I just take sigma star to be the the identity or a two cycle, depending on whether rho star was odd or even, and vice versa. I could take sigma star to be anything, and then just take rho star to be the corresponding even or odd permutation to make sure it works out. But the point is that rho star could be anything, and sigma star could be anything. And this also has to hold for any v in Z3, 8, and any w in Z12 to the 2. Sorry, Z2 to the 12. Mix those numbers up. Z2 and then 12 numbers in total in that vector. So what does that mean? That means that rho star is equal to rho star rho for all rho star. It means that sigma star is equal to sigma star sigma for all sigma star. And the other two cases, v plus rho v star is equal to v star plus rho star v. And w plus sigma w star is equal to w star plus sigma star w. So those are comparing the four components, comparing the 4 components. Here's our big observations. Rho star and rho have to commute. Rho is some fixed permutation. Rho is the permutation for whatever element I'm considering in the center, of which I don't know what they are yet. That's what I'm trying to prove. But rho is fixed. This says that rho commutes with rho star. And it has to commute with rho star for every rho star in S8. What permutation commutes with every element of S8? What permutation commutes with every element of S8? So this is what alludes back to what we proved at the beginning of the course when we introduced permutations. For any permutation on 3 or more objects, there is always something that doesn't commute with it. So that means since rho is a permutation of S8, so of 8 objects, there has to be something that doesn't commute with it. But this tells me that everything commutes with it. So rho can't be a non-identity element. It has to be the identity. Rho has to be the identity, because if it wasn't, I'd be able to find something that doesn't commute with it. So rho has to be the identity. Similarly, sigma has to commute with all permutations in S12, so that means sigma has to be the identity. So right here, we know that if X is in the center, it can't have moved the corners or edges anywhere. It has to be the identity permutation on the corners and the identity permutation on the edges. Okay, now what else do we get? Well, we know that rho and sigma are the identity. So that means that I can do a little bit of reduction with this. This tells me that v plus v star, because rho is the identity, So the identity permutation of V star is just V star. The elements of it haven't been permuted at all. That's equal to V star plus rho star V. But then I can cancel these V stars. They're just being added to both sides of the equation, so I can get rid of them. And I get that V is equal to rho star of V. And similarly, I get W plus W star is equal to W star plus sigma star of W, which is telling me that W is equal to sigma star of W. And these are the big things to keep in mind, because what do these tell us? So since rho star is, maybe I'll say it this way, can be any element of S8, and similarly for sigma star. So this is saying for any element of S8, rho star, if I permute V, I just get the same vector back. So V is equal to rho star V. That tells me something. So this is rho star of V is just permuting. So I got a vector of length 8, and all rho star does is just permute the entries of that vector. And this is saying that no matter how I permute the entries, I never change the vector. So how can that happen? Well, if any two entries were different, swapping them would give me a different vector. So I couldn't have two entries of V being different, because then it wouldn't satisfy this property that V is equal to rho star V for all rho star. So that means that V has to be constant. V is a constant vector. Well, maybe I should say it this way, that V is equal to either the 0 vector, the 1 vector, or the 2 vector. In other words, all the entries are 0 or 1 or 2. So all the entries have to be the same. That's what I meant by being a constant vector. All of the entries are exactly the same. And W equals sigma star W tells me that W also is this constant vector. So it is either all zeros or all ones, because those are the only vectors that when you permute them remain unchanged. Okay, so we're pretty much done here, because now I'm just going to ask a few basic questions. Can all the entries be 1? Can all the entries in vector V be 1? In other words, could all corners be twisted counterclockwise 1 click? What are the thoughts on that? So can V be 1? Can V be 2? Exactly, you got it. No, it's not divisible by 3. So we had this condition that says if you add up all of the components of the vector V, it's got to be 0 mod 3. And the answer is no, because the sum of the VI's would be 8, which is not congruent to 0 mod 3. And again, no, because the sum of the VI's would be 16, which is not congruent to 0 mod 3. So these are big X's. You can't have that. So that means we have that rho, or X, I should say, the element of the center, which is rho sigma V W, is either the identity 0, 0, or identity 0, 1. And that is the things in the center are the solved state and the superflip. And that's the end of our proof. So that's the only thing I wanted to do with this, this group operation on the Rubik's Cube. There are many other things you can do with it. I allude to a couple of things in the textbook itself. You can find a little bit more details about this. Well, one of the other things this chapter has in it is it's saying, okay, the Rubik's Cube group is really big. What other groups can you find in there? Can you find examples of the dihedral group in there? So can you find, a sequence of moves or a collection of moves, I should say, that form a group, and that group is essentially the dihedral group. And it turns out, yeah, you can find instances of the dihedral group in the Rubik's Cube group. You can find cyclic groups of lots of different sizes in the Rubik's Cube group. So if we think of like the dihedral groups, cyclic groups, as sort of the building blocks of groups, the atoms, if you will, the atoms in sort of the group theory chemistry, then the Rubik's Cube is this giant structure, and we can find instances of these other groups inside it. So that's really all I wanted to do with this section. I just wanted to show you this application to get to the superflip, which is quite interesting. Shows us the ability for us to be able to reason through these things and get results without having to appeal to a computer, but computers can also do these things in computational ways. The last thing I want to do is this here, and this is just more of a let's see how far we've come kind of idea. So this was an article that came out a couple of years ago, Popular Mechanics magazine, and it was an online article. And I've only taken a little snippet. The link there will take you to Popular Mechanics. At the time I read it, it was available as a free read. I think right now it might be hidden behind a paywall, so you might have to have a subscription to read the whole article. But I just want to show you the part of the article that intrigued me a little bit. So what the article was about the impossibility of certain things to do on the Rubik's Cube. So things that we very well know all about now after doing this course. So I'm just going to highlight a few things here. So there is no algorithm that flips one edge piece in place without moving any other cubie. We've proven that. Now, we've proven that in a couple of different ways. The final way, we use the fundamental theorem of cubology, and that's because the number of flips has to be even. The number of flips is the sum of that W components of that vector, and that's got to be 0 mod 2, and so there has to be an even number of flips if no other piece has been moved around. And they start to outline this mathematical proof. And so they say something like, when a face of the cube is turned, 4 edges get moved. And so you consider a move where you start twisting faces, let's say 10 face twists in total. Then each cubie is, you follow it around the algorithm, you count how many times it gets moved, and you call that the cubie's move count. And you do that for every cubie, every edge cubie on the cube. So of all the 12 edge cubies, you say, okay, for this edge cubie 1, how many times did it get moved? How many times was it caught up in a face twist? And you do that for all of them, and then you add those all up. And if you add those numbers up for every edge cubie, the total must come to 40 cube moves. And that's because every time you twist a face, 4 edge pieces move. And so when you do 10 moves, you end up with a total of 40 edge cube moves. Each of the 10, since each of the 10 moves adds 4 to the total. And then this is their claim. So in general, any algorithm's total number of cube movies for each cubie must be a multiple of 4. And then they state these critical pairs of facts. If, and this is the one I've highlighted because this is the one we're going to answer. If an edge cubie is moved an even number of times and then return back to the same slot, it must come back with the same orientation it left with. So if I have an edge piece, say I'm following this edge piece here, this blue red one, and I move it once, and then I move it again twice, 3 times, 4 times, 5 times, 6 times, 7 times it's here, and then 8 times it came back to where it started, and it hasn't been flipped. Because I moved it an even number of times, it has to come back to where it started with the proper orientation. That's what they're claiming. If it comes back flipped, it would have had to been moved an odd number of times. And so that's what that highlighted comment made, highlighting of this comment is. If an edge QB is moved an even number of times, even number, it comes back with the same orientation. Odd number, opposite orientation. That's stated as a fact. It's not proven. It's not proven in this article. Although the article was really about trying to prove this, these results about the cube, it actually isn't proven. And so what I want to just do is I want to prove it. And we have the method or the means to prove this in a really simple way, a really nice, sleek, and simple way. And the idea is, I just want to get my picture right. The idea is to just label our, oh, I've lost my picture. Okay, I'll just do it off the fly. So we will draw our cube and we will try to label things so that we can measure rotations, edge flips, in other words. So I need some orientation markings. I'm just going to draw my cube here. And I'll unfold it. I think I usually unfold this way maybe, just to get the back in. Doesn't really matter how we unfold it. There's our back. Here's our bottom. And here's our left side. So what I want to do is I want to label the edge QBs, the cubicles, with an orientation marking, so a plus sign, designate a primary faucet, and I want to do that in such a way that it allows me to prove this result. So my original orientation markings are to put pluses all on the top and all on the bottom, and then just the right and left sides. But I'm not going to do that. I'm going to use a different orientation system, because this different orientation system is going to be a means to proving this result and not the fundamental theorem of cubology. This is more just an edge-specific result. So here's what I'm going to do. I'm going to label my pieces like this. I'll put them in a different color just so they pop. So I'm going to make that a plus. And then I'm just going to alternate. I'm going to imagine if I do a right face twist, that plus would come down to the front. So I'm going to take the opposite as my primary orientation. And I'll do that as I go along. Then I'll make that a plus, and then this a plus. So you can see on the right side, I've now labeled the 4 edge cubies with their primary faucets. And I've just alternated sort of inside, outside kind of thing. And we just keep doing that. I'll go around the puzzle like this, where it's always the opposite ones that are sharing the same face, and then the ones in between flip to the other side. Let's see if we get them all. Something like this, and then I need this one here, and I need this one down here, and that should be it. There should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, got 12 plus signs, so I've hit the 12 locations. And now with this orientation, I'm gonna conjure up something. Think checkerboard on the 15 puzzle. Remember, we used the checkerboard on the 15 puzzle to talk about odd versus even moves away from the space 16. So with these markings, every move, the front, back, right, left, up, down, switches orientation of all edge cubies. And so every time you move, the orientation switches. So in order to start at the same spot that you're going to end at, and to have the same orientation, you have to move an even number of times, because every time you move, the orientation of your edge QB is flipped in relation to the orientation marking. So to return to where you started with same orientation, edge QB had to move, edge QB had to move an even number of times. And vice versa. If you move an even number of times, then when you get back to where you started, you have the same orientation. And that's it. That's all we need in order to prove that result, was just to label our cube in a way that we could now say that anytime you move an edge QB, one click, it switches orientation. And so we can play with these orientation markings and modify them. The one I gave to do the fundamental theorem of cubology is not the be-all, end-all. There's ways to modify it to prove other things that are of interest on the puzzle. So now we've got a new fact. We've got that if an edge QB moves an even number of times and returns back to the same slot, it has to have the same orientation. So if you're going to want to flip a QB, you're going to have to move it an odd number of times before you come back to where you start. All right, so that's it for the Rubik's Cube. That's basically all I want to do out of the book as well. So we've technically officially wrapped up all the topics. On Friday, I think what we'll do is we'll do the Futurama episode and play around with that a little bit, and we can answer any questions about homework assignments or even the projects that are coming up in the following week. All right, I'm just going to stop the recording now.